Hi, we have been talking about the Heisenberg group, only the one built on R3. And in this video, I want to cover an aspect of it that is not mentioned in many places, and that is how on earth one would come up with this weird multiplication. It's not even clear if this is a group operation. For example, you have to multiply 3 elements and check that it's associative and whatnot. By the way, this group multiplication is not commutative. If you put XYZ first and then ABC next, you get a different outcome. So unlike the common operations on R3, this is non-commutative. A times B is not B times A in this world. But anyway, so there are two answers, and number one is that this group H1 with this multiplication that you see is isomorphic in the sense of groups. So from point of view of multiplication, it's basically the same as the space of matrices that have the form of 1 on the diagonal, zeros below it, and then A, say B and C. So think about all such matrices where A, B, and C are real valued. So this is actually then as a set is in bijection with R3. And then with the usual matrix multiplication. The very way that you multiply matrices in the usual sense. And if you do that, you will realize that it has some, it's reasonable to believe that this is isomorphic. Of course, to prove it, you need to write down an isomorphism. I have done it before in my life, so I'll let you also enjoy that. So A prime, B prime, and C prime, if you put them here, then so this will remain upper triangular. Here you will have A plus A prime. Here you will have B plus B prime. Here you will have C plus C prime, but also A times B prime. Similar to the Heisenberg group multiplication, the third element also borrows stuff from the previous two elements. As I said, this is only an isomorphism. It's not exactly same multiplication, but from the point of view of groups, that explains it. Actually, there are some variants of this multiplication which only uses, say, bx and not both of these. But all of them are isomorphic. So that is one way of why on earth would one think about multiplying elements in R3 like this. But then there is also a more kind of a deeper reason which I wanted to emphasize in this video. And that is you begin with nothing other than a Lie algebra. So what is a Lie algebra? A Lie algebra is a vector space. That means you have a scalar multiplication and addition of vectors, right? A v1 plus B v2 makes sense in this space. For our purpose, of course, you can imagine it's a real vector space. The field is just the real numbers. But why don't we call them vector spaces? Because they have one additional structure, and that is what we call a bracket operation. So what is a bracket operation? It's a function from the vector space. So usually we use funny letters to designate Lie algebras because we want to use the G for the group. So this G is, I want to make it like squarish. So this G is the Lie algebra, and then a bracket is a binary operation from this product of this vector space to itself. So and we don't give it a name, rather we really represent it with bracket. So that means given two vectors in this space, v1 and v2, we find the third vector in the space, which is called their bracket. Of course, it's not just any assignment of vector, it has to satisfy certain properties, and because that's not the point of this video, I want to just cheat and show you those real quick here. So a Lie algebra is, as you can see from this Wikipedia definition, so it's a binary operation like this, as I wrote. It's bilinear, so the nice properties we expected, that with respect to this scalar multiplication, you can bring them out of bracket. Any vector bracketed with itself has to be 0, and most important property usually is this Jacobi identity, that if you bracket them you get a vector, so you can put them again back in the bracket with a third vector, and if you do this in a cyclic order, you add them up, you always end up with 0. From these follows an important property, and that is the anti-commutativity. If you reorder x and y, you have to multiply by a negative. Multiplying by a negative, remember, makes sense in a vector space. So this is it, the vector space plus some operation like this. Now, what does this have to do with Heisenberg group? So we are going to construct Heisenberg group by starting with its Lie algebra. So the Lie algebra of the first Heisenberg group is R3, so it's a vector space, as a vector space, with the bracket, so with the bracket operation that E1 bracketed with E2 is E3. So here E1 to me is 1, 0, 0, E2 is 0, 1, 0, and E3 is 0, 0, 1. So for now, we don't know what this is. We want to recover it. So all I'm telling you is that suppose you have R3 with a bracket whose only non-trivial bracket is this. That means any other bracket will be 0. So E1, for example, and E3 will have to be 0. E2 and E3 will be 0. And by this linearity, bilinearity, and commutativity property, you get all other quantities that you want. Of course, E2 and E1 will be negative E3, and like that. So this is kind of the simplest non-trivial bracket that you can introduce. Just one non-trivial bracket and everything else is 0. So if you didn't have this one, then the bracket would be the trivial 0, 0. Okay, now you have just a Lie algebra. We want to get to a Lie group, because remember H1 is a Lie group. And here is where there are important theorems in, well, the space. So this is a fact we need to know. And we call the space of left invariant vector fields on a Lie group form a Lie algebra where this bracket comes from, so manifold theory. So in this case, this bracket has a geometric meaning in terms of flows of vector fields or in terms of derivations, but we don't want to get into that. So one natural setting where we come across Lie algebras is whenever you have a Lie group, then the tangent space to it, either you can tell the space of left invariant vector fields, or equivalently you can just say that the tangent to the group at the identity. We can identify these two worlds. And so every time you have a Lie group, the tangent space at identity is a natural Lie algebra. So how about the reverse? And that the reverse is what we are interested in, because for now we imagine that we don't know what is H1. We don't have the Lie group. We only have this kind of made up artificial Lie algebra. So can we move from Lie algebra to a Lie group? And that is in fact true. So basically it's saying that to every Lie algebra we can associate a Lie group. So we can always find a, if you give me a Lie algebra, I can find a Lie group whose tangent space at identity with the bracket coming from the manifold theory is isomorphic, is a copy of the Lie algebra that you gave me. And if I induce some assumptions such as simply connectedness, then basically up to isomorphism, this Lie group is unique. So let's add that also there because that's very important. So basically a Lie algebra also determines a Lie group. The reverse, that a Lie group identifies a Lie algebra was more direct. And that is called the third correspondence theorem. There are 1, 2, 3 correspondence theorems between Lie algebras and Lie group. So let me see where this was. Okay, the correspondence. So you see here there are a few results here. The Lie's third theorem: every finite dimensional Lie real, that means based on real line, Lie algebra is the Lie algebra of some simply connected Lie group. And there is this uniqueness part that is not mentioned here. So we are one step closer to finding our H1. We started with this artificial Lie algebra here, and now we know there is some group. So there is some group which I already denote by H1. It's going to be our Heisenberg group. Of course, a Lie group whose Lie algebra is, well, in mathematics, is means up to isomorphism, isomorphism of Lie algebras, which means a vector isomorphism that respects also the bracket is isomorphic to the Lie algebra above. That means the tangent space at identity of this G is a copy of R3, and there is a bracket operation that is exactly this one here, that E1 and E2 give E3 and other brackets are 0. Now, how useful is this? Not that much, because what is this group? How do you multiply elements in G? And that's not obvious from this, but then there is the magic coming from what is called the Baker-Campbell-Hausdorff formula. So what does this formula tell us? Here is the thing. You can always there is a map called the exponential map that takes an element of the Lie algebra, the vector, the tangent vector at 0, to an element of the group. So there is this connection, and if you have this simply connected thing, this will be a bijective map, and it's also smooth and whatnot. But all that is important to us is that to every element in the Lie algebra, we can associate an element in the group. And vice versa. Every element here, let's say little x, so for every element in the group, there exists some x in the Lie algebra, a vector, such that the exponential of capital X is the little x. So we are in the world of simply connected Lie algebras. This exponential map itself is also unknown to us at this moment with this abstract setting. But the Baker-Campbell-Hausdorff formula that I mentioned, and I will go back in a second, answers the following very, very important question. Suppose you know that this element x comes from the exponential x, a vector, and your element y comes from the exponential of another vector of y. Can we find z in the Lie algebra such that x multiplied with y, this multiplication is happening in the capital G, in the group. So we know that this is exponential of some, this is a new element, so this is some little z in the Lie group, and we know it comes from exponential of some vector. But the question is, can we identify this z? Can we solve this question? What is that unique element z in the Lie algebra whose exponential becomes the multiplication of x and y? Of course, by this can we find z means in terms of capital X and capital Y. We know x and y, we know their images under exponential, and we want to find the new vector whose exponential will be their multiplication. And Baker-Campbell-Hausdorff formula is an amazing answer to that question. So what I explained is written here in the first formula, e to x, e to y equals e to z. Then this formula says that your z will be this infinite summation. Of course, part of the claim is that this infinite summation converges to some vector. And then you identify z in terms of just x and y and their brackets. And it's not even clear from just these terms how you would construct the fifth and sixth terms. But of course, there's the more explicit formula down here, as you can see. But we don't really have to deal with an infinite sequence because our brackets will die out sooner or later. Remember, in our setting, we have only one bracket that is non-trivial. And here you see that x and xy, y, in the last one, y and xy, so y repeats, here x repeats. So ultimately, you will end up having repeated elements, and we know that bracket of any vector with itself is 0. So in our case, in fact, anything after this 1/2 bracket xy will disappear. So these 1/12 and minus 1/12 and anything after them are all zeros. This will be, of course, true whenever you have a Lie algebra that when you keep taking brackets in finite time, everything vanishes. Then this will always be a useful formula, because then the infinite sum becomes just a finite sum. So in our case, then, if we apply this Baker-Campbell-Hausdorff in our case, gives that E2, so exponential of E1, exponential of E2 is E1 plus E2 plus 1/2 bracket of E1, E2. And you're feel free to write out the following terms and check that actually you get zeros. So this becomes E1 plus E2 plus 1/2. This will be E3. Right. Now, as for the H1 operation, what you want to do, so finally, can we use this to exactly write down the group and the multiplication in the group? The answer is yes. How do we do that? We identify this G with G. This is very tricky, and this identify here, let's say just as sets, because G is a group. This one is a Lie algebra, so there is no natural definition of an isomorphism between them. But here you just make them superficially the same as sets. And the other way of looking at this will be that we make exponential to be the identity map. So if we have this bijection xp between G and this G, this Lie algebra G, then because it's just the set bijection, we can simply identify things. So anything in the image is identified with its preimage. It's a bit crazy, but we have to keep separate. It will be okay if you just think about it as being sets being in bijection. And then the tricky part here is that previously you could imagine that this is your Lie algebra, this Lie group. So it could be, say, bent in the space, but the Lie algebra is the tangent at the identity, right, as a vector space, the space of vectors. With this, an exponential is like this. So you have the vector here, and then its exponential becomes the point here. So capital X, little x. Under this identification, what you're doing is that you had this G as your Lie algebra, as your vector space, but all of a sudden you put a copy, so this is the origin, and you put a copy of G here. Now this larger G, you think of it as the group, and this copy at the origin, you think of it as the tangent to G at 0. Although both of them are the same object, which is a copy of R3 in our case. So it's like you have one Euclidean space, and then just at the origin you have a tinier copy of it, just to help us visualize. Otherwise, they are both same size. There's no tinier R3. So under this identification, now exponential is the identity map. And of course, this little g, the way I draw it, is not in any way tinier. It's just, again, a copy of R3. So any vector here, x, can be seen also as the tiny x. Now, if you do this identification and then try to write out multiplication in Campbell formula, you will recover the Heisenberg multiplication. Let's try it. So suppose you want to do multiply a, b, c. You want to multiply it with x, y, and z. So Hausdorff-Campbell will say that this is exponential of something times exponential of something, and if you write it out, then you will recover it. But exponential is the identity map, so this is the same as ABC again. But you can think of it as a point in R3, which is your group. But now we have to treat it as a vector. That's why I want to write it E1 plus BE2 plus CE3. So this is a vector in the Lie algebra. Of course, they are the same things, but remember, even in doing basic calculus, sometimes it's important to treat sometimes a value as a point and all other time as a vector. E1 plus YE2 plus ZE3. Now comes this Baker-Campbell-Hausdorff formula. So exponential of two objects was just add those two objects. So add these two vectors, it will be a plus x E1 plus b plus y E2 plus c plus z E3. And then you have 1/2 the bracket of them. So this will be, let's write this out, BE2 plus CE3 bracket XE1 plus YE2 plus ZE3. But what survives this bracket? Number one, it's bilinear, so we will just put out the, we can do individually. So take this and bracket it with everything here. So E1 with E1 is 0, E1 with E3 is 0. The only remaining one is E1 bracketed with E2. And the scalar values are AY. So you will have AY 1/2 and then E1 bracket E2. And then take this and bracket it with everything. If you bracket this with E1, so you will have 1/2 B from here. Now I'm doing this one, B with Y, sorry, B with X, and then bracket E2, E1. Remember, you have to respect the order for bracket. And then, okay, E2 with E2 will vanish, E2 with E3 will vanish. Then you will get 0 because bracket of E3 with everything is 0. This is just the bracket part, sorry. Let me see. This bracket equals this. So if I replace it in the formula, I get that a, b, c dot x, y, and z is, so I had for E1, I want to write it back as a point, not a vector. I'm kind of applying the exponential. So, well, in fact, I need exponential. So the exponential of this whole vector. And after, when I apply exponential, it's identity, but I basically drop the vector notation and write it as a point. So for coefficient of E1, I will have a plus x. Remember, this will be E3, and this will be negative E3. So these don't affect E1. The coefficient behind E2 is b plus y. What is coefficient behind E3? It's c plus z plus 1/2. Okay, we had this, so I wrote this one. These are gone. And now from here, I have 1/2 of ay. And this is minus 1/2 of bx. And there you go. This is the multiplication on R3, whose Lie algebra is this bracket we started with. So we started with a tiny Lie algebra, R3, with this bracket that only E1 and E2 becomes E3. From this was the Lie algebra. We constructed the Lie group, but then we identified it back with R3. And then we used Baker-Campbell-Hausdorff formula to construct the multiplication on G out of the bracket. Now, this is not exactly the multiplication in Heisenberg group that we had. We had actually 2 here, and I think also we had a plus minus difference here. But that comes from the fact that to make my Lie algebra the simplest, I had that E1 and E3 is, E1 and E3 bracket is E3. But remember, for our Heisenberg group, the way we introduced it, it was that E1 and E2 was negative 4 times E3. Remember, we had this x and y bracket is negative 4, t being the vertical axis, x and y being the usual ones. So, but of course, if you start with this, then why put negative 4 up front when you don't know why you're putting it? So this is just so this is an isomorphic definition of Heisenberg group. Actually, as a group, these are isomorphic, and their Lie algebras are isomorphic. So a Lie algebra on R3 where this is equal to E3 versus a Lie algebra on R3 where this is equal to negative 4 are just isomorphic, basically. And even from general theory, it follows that if you have isomorphic Lie algebras, the Lie groups that you produce out of them will be also isomorphic. That's another non-trivial fact about Lie groups, correspondence with Lie algebras. But anyway, if you strictly wanted to find the multiplication, the very multiplication up to every sign and every value number for the Heisenberg group, the way we introduced it, you would go back, and instead of having this bracket equal to E3, you would have equal to negative 4 E3. And then you would exactly recover our formula. But of course, in some texts, actually, they just take this multiplication to be the very definition of Heisenberg group. So, long story, I didn't anticipate this video to be this long, but I'm very happy for it, because this is a thing that is not mentioned everywhere. Like, why on earth would you just define a multiplication on R3 this way? How did you even know this will end up being an actual group multiplication? So this is very natural. That the matrix thing is there, of course, but I find this other one also very satisfying theoretically. So we start with the Lie algebra, the simplest out there. From that, you produce a Lie group, and then there is the amazing Baker-Campbell-Hausdorff formula, which tells you how to really construct the group action, the group multiplication out of the brackets. Hope you enjoyed this. If you have any comments, please put them down there. Subscribe if you haven't yet, and see you in next videos.